So in this video, we're going to tackle a fun little problem, which is to take a BST and actually draw a little picture of it, or render the BST as an image. So I'm in render BST starter.racket, and it starts just with the BST data definitions that we've had from before, and this little picture that I drew using a drawing program with its examples. But then it says, design a function that consumes a BST and produces a simple rendering of that BST, with an emphasis on simple. You might want to skip the lines, for example. So let me show you how I did that. Since it's about rendering, the first thing I did was to get out a pencil and paper. And I drew this little sketch, which is basically just a replication of the sketch we had from before. And I started thinking about how I might make it simpler, and I just followed the suggestion from the problem statement, and I redrew it without the lines. And when I redrew it without the lines, things got closer together. It doesn't look quite as good, that's for sure, but it still kind of has a tree structure to it, a binary tree structure to it. But then I wanted to know kind of, well, what's really going on in there? And we know this is going to be a recursive function operating on the tree. And whenever we have recursive functions, the actual function itself just does one level of the recursion. It deals with the natural recursions, or it lets the natural recursions do the rest of the work. So we really just need to focus on one level of the drawing. So what I did then was I drew this picture. And in this picture, I'm calling render on the root of the tree, the 10y node in the tree. And what I've got with these boxes are just to say that, look, the rendering of 10y is just 10y, and then the rendering of the left branch and the rendering of the right branch, whatever they are. And I just drew some boxes around them to say whatever they are. And I realized, in order to make the picture maybe a little bit less cluttered, I could put a little bit of space between the left and right tree, and I called that H space for horizontal space. And I could also put a little bit of space between 10:y and the two subtrees, and I called that V space for vertical space. And I realized that there were a couple more constants, like the color of the text and the size of the text, and what actually goes between the key and the value. Is it a colon, or maybe it could be something else? And so now I really feel ready to turn to the code and finish the design of this function. So what I'll do is I'll add a constants block to the program, and I'm just going to basically read this right out of the analysis. We'll say that text size 14, let's say. Text color is black, let's say, and we'll say the separator, I'm going to call it the key val separator, is a colon for now. And let's just say that the vertical space, let's see, this is the space that's going to go between the key value and the two subtrees. So let's just make a little rectangle for that. And since it's vertical space, we'll make the rectangle narrow but 10 high. And I don't know if 10 is the right number. As with all constants, we can change it later depending on how it looks. And the H space, let's just make the H space be exactly the other way around. It'll be, H space, there's a P there that doesn't belong. The H space will be 10 by 1. And that looks pretty good. There's my constants. So now let's go down and turn to the actual function that we want to write. Got a function separator all here already, so we're all set. So let's see, this function's got to consume BST and produce an image. And it's just going to produce a simple rendering of the tree. And here's the stub. And it's just got to produce some blank. Square, 0, solid, and white. So far, everything's well formed. Okay, let's do the check expects. Let's see, the first one, check expect render BST. Now the base case for a BST, as you remember, is false. So let's do that, render BST of false. So what do we want that to look like? Well, I don't know, that's just a white box of some sort. You know, that seems like a constant quantity that's important. So let me go back up here and put it in constants. And it's just going to be define, let's see, empty tree is going to be, I don't know, let's make it a rectangle that's 20 wide and 10 high and solid and white. And if this turns out not to be the right shape or size, we can change it later. So check expect render BST false should just produce that. So that's the base case. Okay, let's see. Let's do 1 ABC. That's node 1. I'm pretty sure we have a constant for node 1. Let's go C. Remember, clicking here gives me a list of everything that's defined in the file. And there is a constant for BST1. I could go look at it if I need to. I don't really need to in this case because once it's defined, I can assume it's defined right. Render BST, BST1. Now what's this going to look like? Well, let's see. We know we're going to append or string append 1 and the key val separator, which is probably colon, and ABC. We're going to put all those together. And we know we got to turn that into an image. So that gives us that top line, like 10 WHY. What do we do with that? Well, remember, that tree actually has two null children. It has 2 children that are false. So that whole text there has to go above the rendering of those 2 children. And of course, we talked about how we leave some nice space to make it look a little bit better. So there's going to be the V space. And then there's the 2 children next to each other with the H space between them. So that's beside the first child, the H space, and the second child. So now what's the first child going to be? Well, this is just going to be the rendering of false. Now I got 2 choices here. I could put empty tree, because I know that's what it's going to be. Or let me show you something else I can put because it's going to be helpful later. Because I've already tested render BST with an argument of false, I can put that because I've already tested that as my first test. And this, in fact, is what's going to happen here. Node 1 has false as its left and right childs. So what it's putting below it is the rendering of false, a little bit of H space, and the rendering of false. So there's my second case, and now I can run my tests. And they're both failing. And remember, the great thing with image tests is you can let them fail, but look at the images to see if they look right. Now I'm sort of eyeballing my check expects to see if they're sort of look the way I want them to. And that there looks pretty good for the rendering of an empty tree. It's just a white box, but it's got a little bit of size to it. And that looks pretty good for the rendering of 1 ABC that has only null children or empty children, or no children in some sense. That's what the interpretation says. False means nothing there at all. So that looks pretty good. Let's keep going. Let's see, I've done the false case and I've done the 1 ABC case. Let's do a more complicated case now. Can we go? Let's go all the way. Let's jump all the way to check expect render BST of, now we'll do a node that has some children. Let's say BST4. Is that one that exists? Yes, it is. So BST4, we're going to render that. Now what's that going to look like? Well, it starts out a lot like the other one, string append 4 and key val separator and DCJ, text size, text color, And that's going to go above a little bit of V space and a beside. Now what's the left child of DCJ? Well, that's a false again, so render BST of false. And then some H space. And then what's the right child? Well, the right child is this 7RUF. But you know, that's a case exactly like ABC. So I've already tested that case. So instead of having to construct this whole thing in a complicated way, I'm allowed to just call render BST here with make node 7RUF. Because I've already tested that render BST given a node with no children is producing the right thing. That was this second test. So because the first test tested it with false, I'm allowed to call render BST with false in the second test. Because the second test tested it in a case where both children are false, I'm allowed to call render BST with a node in which both children are false in the third test. This is making these tests a lot more compact than they would be otherwise. Otherwise, I'd have to accumulate all this stuff as the tests get bigger and bigger. Let's just run this test first, make sure it's well formed, because it's not. There's supposed to be 4 arguments here to make node. There's a false and a false. Should have known that, since the whole point is it's a test with 2 false children. Great, now my tests are running and failing, and now I can look at how the third one looks. Now I don't get to see exactly how it looks because this call to render BST isn't really working yet. So I'm not really seeing exactly how it looks, I'm just seeing the beginning of it. But I get some sense of it. Let's go do one more case. Let's do BST3, which I'm pretty sure exists. It does. So BST3, now this is a node that's got 2 real children. We haven't had one of those yet. Text size, text color, a little bit of V space, and then beside of a. Now what are we going to do? We're going to render BST of BST1, that's 1 ABC, and then some H space and then some H space and render BST of BST4. That'll be that case. And now when we look at it, we really don't quite see what we want because really we've got 2 recursive calls that aren't really doing anything yet because we're just running against the stub. So we're really only seeing the root. We do see some mistake I made here. What happened to the value there? Oh, yep, right there it is. It is always good to run the test as early as you can. That's supposed to be ILK. Okay, so now we've got 3 tests. Let's get our template and finish up. There's the template. Bring it down here. We rename the template function. It's got natural recursions in it, so we rename both of them. We'll get rid of these because we know those now. Now let's see. Make a little bit more space to work here. Our first test tells us, remember it's serving both as a test and as an example. It's an example of what we want. It tells us that in the case where the tree is false, we just produce this special constant called empty tree. And then this is another one of those cases with these image functions where working out the examples was really the hardest part. Now that we've got the examples, we're really done. We know what the layout is. The layout is just what it says here. We're going to take the key and value and we're going to string append them together with key val separator, and we'll get rid of some white space here, and we'll get rid of some white space here. We're going to do that. We're going to turn both of those into an image. And then we're going to take that image and we're going to put it above a little bit of V space. And here's the two natural recursions, and what happens to them? Well, they go beside each other with a little bit of H space in the middle. Fix the indentation. Oh, once again, I keep saying string instead of string append today. String append expects a string as the first argument and it got 1. Oh, right. The key is a number. It's not a string. I have to turn it into a string first. All 4 tests pass. See how easy the function was to actually do? I made a couple little boo-boos, of course, but aside from that, the combination of the template and having worked out the examples made the function itself really easy to do. And now if I say down here, render BST of BST10, that's the big one, that's the image I get. It doesn't have the lines in it, but it still clearly looks like the tree. What we're going to do in a couple weeks when we learn one new language construct is we'll go back and put the lines in it. So there you go. What this video is showing is it's another example of taking one kind of recursive data structure and turning it into something else. In this case, we take the binary search tree and we produce an image. The image has the same tree-like structure as the tree itself. And it's also an example of how getting all your examples first and then having the template means that when you finally get to coding the details of the function, it's not that hard.